I'm very excited to have Vi Hart visiting the office over here, and we were just having a very mathematical conversation earlier today, and she mentioned something that is fascinating.
Yeah, I was just telling Sal about a cool thing called Benford's Law.
Benford's Law, and what is Benford's Law?
It's this weird phenomenon that you get when you're looking at numbers in the real world. So, for example, we've got some graphs here. If you take the populations of all the countries and you say, all right, what is the first digit of the population of the country, whether it's 1 million or 1,000 or 100,000, we'll say, okay, that starts with 1. So we'll count up all of the countries that start with 1. And I guess here we've got 27 of them.
Yes, about 27. So literally, like anything that starts with a 1 here. So it could be a country that has a population of 1, a population that has a population of 17, or a population of 1,300,000,000, blah, 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 blah. They would all fall into this bucket right over here.
Right. And then if you start with 2, you fall in the second bucket, and so on and so forth.
A better color. Oh, yeah, go ahead.
Yeah, definitely better color.
Better color,
oh, that's
yeah,
great.
yeah, that's the blue, better contrast.
So the question is, all right, you'd think you'd have kind of random numbers here.
Yes, for that first digit, like it's kind of random.
Yeah, I mean, there's huge differences in populations of countries. Some have
Right.
billions, and some have I don't know what the smallest population is.
Yes,
but
it's like Montenegro or something like that.
yeah. So
No, Montenegro's not a country. What am I thinking? I'm thinking of what's the one that's on the French River? Anyway, we can edit that out. All right.
I don't know. I would be interested to see for populations of states and everything.
The Vatican is the smallest country, I believe.
Yeah, does that still count? I guess
I think the
depends how you
Vatican
count.
counts. They have their own, yes.
I don't know exactly
yeah.
what the requirements
Okay,
were to be.
but it
to
would
get
include
yourself
the
into this
Vatican,
graph.
which I think would
It
be in
would.
like the thousands.
Yeah, and so why would this happen? Why would you see more 1s than 2s? Like,
Yeah,
what is going on?
It's not some small chance. I mean, we were talking also about the idea that it is more likely to have odd numbered addresses than even numbered. We were talking about that earlier.
Yeah, I just learned about that recently.
Yes, but that's not
and
a
that
huge.
Makes sense.
That makes sense because every house will have a number 1 on it.
Right, every
or
street.
10.
If your street starts, with house number 1, house number 2, house number 3.
Right,
if you have an odd number
yes.
of houses, then your street has more odd numbers. Than
Exactly. And if you have an even number, you have the same amount.
Right.
Right.
But that's starting with 1, which is odd, whereas here, populations don't start with 1.
Exactly. And that phenomenon that we're talking about with the street numbers, it's not an extreme phenomenon. It's like 50 point some it's a slightly more, you have a slightly higher probability of having an odd numbered house or I guess a 1 house than everything else.
Yeah, it's kind of exactly what you would expect.
It's exactly what you expect. But here it's a significantly higher probability of a random country's population that its first digit is a 1 versus its first digit is an 8 or a 9. I mean, it seems a little bit strange.
Yeah, and this isn't just in countries.
Yes.
You see this if you're looking at a lot of financial stuff, like
Yes,
how much money does a company make?
Yes, the ones just show up as the first digit much more frequently.
Much more frequently, yeah. And here we have another fancy graph, which is like completely crazy. It's the first digit of physical constants. So what would be examples of some physical constants?
Like I'm assuming that there, and we weren't able to figure out exactly what they applied here, but I'm assuming it's things like the gravitational constant, Planck's constant, and this seems kind of crazy to me because it depends on the units that you're using. It depends on a whole bunch of things that you have to assume about it. But even when you use these kind of arbitrary physical constants, which I'm assuming they're doing here, the most significant digit in these physical constants is still much more likely to be 1. It almost exactly follows Benford's law, and it kind of gives you goose pimples. So
the challenge here is to. Oh, by the way, Benford is the guy with the glasses.
Oh
there.
yes. You might be wondering. These aren't. Yes, these are these.
They're not both Benford. But
These are not
Benford.
Pre shave and post shave. No.
No.
This right here is Benford, and obviously it was named after him, Benford's law. But we put this gentleman who didn't shave.
Yeah, the cool guy with the beard is Simon Newcomb.
Simon Newcomb. And
not Duke Nukem.
Not Duke Nukem. And we put him here because he's actually the first person who stated Benford's law. He obviously did not call it Benford's law.
And he had the better beard.
And he had the more he was overall more imposing character. At least to me. This
Yeah.
guy looks a little bit like Harry Truman. Maybe this is Harry. I don't know. I don't know. That's maybe I've got the wrong picture. Anyway, let's just.
So the question is, what is kind of the pure case of this? I mean, when you got this random data, you see some fluctuations. Like in our
Right.
country, right? There are.
It's pretty close
more
though. It's pretty
countries.
close. It's pretty close.
Yeah,
to
and our
that
sample
curve.
size is pretty low. I
Right,
mean,
right.
When you've only got
200 countries or something like that. Yeah.
Yeah,
It
so
went up by
it
like
doesn't
15
perfectly
after the
follow it.
Soviet Union fell and all of that. But yeah, it's not a huge number of countries. And even physical constants, I don't know how many physical constants they randomly sampled over here. But it is shockingly close to Benford's law curve. But there's kind of a more pure way of studying it.
Right. So when we look at this other graph, this is kind of like the pure Benford's law.
Pure Benford's law. So that's this curve that that we're kind of fitting to that other more rough data.
Mm-hmm.
And what's amazing here is that if we take kind of pure mathematical constructs like the powers of 2 or
the Fibonacci series, if you'd think that in the Fibonacci series you're adding all this stuff up, and why?
and you just take the first digit,
just the first
and,
digit,
and put them in these piles, it would actually exactly match Benford's law, like no deviation. It is exactly
right. Mathematically. It's
mathematically. So let's just be clear, because this is fascinating. So if you were to take the powers of 2, so you get 1, 2, 4, 8, 16, 32, 64. I want to go pretty high so you can start to see how we're doing this. 128, 256, 512. And you just keep going on and on forever with every power of 2. And you say, okay, how many of these start with a 1? And you would go and you would say, well, this starts with a 1. This starts with, or the most significant digit is 1. That starts with a 1. That starts with 1. And you would just find the percentage that start with a 1. And then you would plot it on you would give the ones that credit for that percentage. And then you'd say, okay, the ones that start with a 2. And you say, okay, that starts with a 2, and that starts with 2. But we want to keep going on this, and we could probably do this with a computer program or something where we go really high powers of 2.
Mm-hmm.
And then you would say, what percentage of all of these powers of 2 start with a 2? You would say, get this percentage right over here. This probably the number that start with a 9, you would get this. And you would perfectly match Benford's law.
Yeah.
This seems magical.
It does seem pretty magical.
And Fibonacci, and this isn't just for powers of 2. This is powers of any number.
Almost any number.
I
There's
believe
special
it might be
cases.
every number.
Yes, powers
not.
of 1.
1 would not work.
And then there's
right.
like powers of 10.
Powers of 10 would not work as well. Yes, but every other numbers that
Powers
kind of
of
mix it up a
0.
little bit. Yes, you are correct. Every number that would mix it up a little bit.
Yeah, it has to have a certain amount of mixing it up a little bit.
Right. But they would exhibit Benford's distribution, and so we want to challenge you to think about why that is, and maybe you could even put your own explanations in our little message board on either YouTube or our page if you're curious. But we'll challenge you to think why that is, and then we'll offer at least a decent shot at an explanation. Maybe we'll have other explanations.
Yeah.
So actually, we'll leave you there in this video, and in the next video, we'll explain why we think an intuitive reason why it works.
Mm-hmm.